this is hopefully the last video. I believe this makes video number 7 on convergence and divergence tests. It's part 2, or video number 2 of convergence and divergence test part 3. So video 2 of part 3. And so in this video, we're going to be talking about both the integral test and the p-series test. So the way the integral test works is that if you have a function that is positive, continuous, and decreasing, then what we know about that function on the closed interval from k to infinity is that if the integral from k to infinity for the function is convergent, so this goes back to our improper integrals that we learned about in the last unit, then that means that the series from n equals k to infinity using that function as the expression is also convergent. So how do we use that? Well, a really good example of it is the sum from n equals 1 to infinity for 1 over n squared. If I look at just the function f of x equals 1 over x squared, the graph of that function is positive, continuous, and decreasing beginning at an x value of 1. So it looks like this, which is positive, continuous, and decreasing, starting at n equals 1. If I looked into negative values, then I actually end up with a curve over here as well, which is not decreasing, but we don't care about that because we're starting at an x value of 1. So because that function is positive, continuous, and decreasing, I can use the integral test to prove that this series here converges. So I would do the integral from 1 to infinity of 1 over x squared dx. Now, since one of the boundaries is infinity, I do have to do this as an improper integral. So I would do the limit as b goes to infinity of the integral from 1 to b of 1 over x squared, or of x to the negative 2 dx. So that's going to integrate back to the limit from as b goes to infinity of negative 1 over x from 1 to b. So continuing to evaluate that, I would have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. So with substitution, we get negative 1 over infinity plus 1, or 0 plus 1 is 1. So what the integral test tells us is that if I get an answer for this improper integral, something other than infinity or divergent as an answer, then because the integral converges, the series would converge as well. So we would say, therefore, the sum from, what letter did we use? N equals 1 to infinity of 1 over n squared converges by the integral test. But that only works if the function inside of the expression for the series is positive, continuous, and decreasing. That's the only reason why you could apply the integral test to it. Now, it also shows that if the integral is divergent for the function, then the series is also divergent. So here's another good, easy example. We already know that the harmonic series, 1 over n, is divergent. I've proven that to you previously. But here's another way that you can prove that it's divergent. Our function here would be 1 over x, which the graph of it also looks like this for x is greater than or equal to 1, which is positive, continuous, and decreasing. Therefore, the integral test could be applied to it. So the integral from 1 to infinity for 1 over x dx, I would have to do an improper integral for it. Now, 1 over x integrates back to natural log. So we end up with the limit as b goes to infinity of the natural log of b minus the natural log of 1. When we evaluate the limit, the natural log of infinity is infinity, and the natural log of 1 is 0. So we get an integral that is divergent. So this is yet another way that you can prove that the sum from n equals 1 to infinity of 1 over n diverges. Okay, so that wraps up the integral test. I think that's a really good and useful test in a lot of situations if you realize that the improper integral would be useful. So the final test that we're going to look at, which is a super easy test, and I like it a lot because you can just look at it and kind of know what's supposed to happen. If you have a series that's of the form n raised to a power, like 1 over n to the second, or 1 over n to the first, or 1 over the square root of n, this should be a negative right here, or 1 over n to the negative 2, simply looking at the value of that exponent will tell you whether or not the series will converge or diverge. If your exponent is greater than 1, the series will converge. If your exponent is less than or equal to 1, the series will diverge. So for all 4 of these, 1 over n squared, p is 2, which is bigger than 1. I just proved a minute ago, using the integral test as well, that this series would converge. But now I don't have to use the integral test for it. I could just say it converges by the p-series test. This one I also just proved a minute ago diverged. Well, its p-value is 1, which falls into the diverge category from the p-series test. 1 over the square root of n, its p-value would be 1/2, which is less than or equal to 1. So it would diverge. And I could use the integral test to prove that if you wanted to. In addition to the p-series test, there's other tests I could use too, but the integral test would prove why that works. Pretty much the integral test supports the p-series test in every situation. And then lastly, with 1 over n to the negative 2, p is negative 2. We don't look at the absolute value of it like we do with the ratio test. We look straight at it. So negative 2 is less than 1. So this guy also diverges. Okay, and again, all of those could be proven with the integral test additionally. All right, so that wraps up all our tests for convergence and divergence.